Of course, we're very happy to be here too. Many thanks to the Institute for hosting us, to the program organizers for making this all happen, and for the workshop organizers for inviting me to speak. So I would like to talk about some ongoing joint work. I've been talking with Jeremy Hahn here this spring, and he had talked with Sanath Devalapurkar earlier, and we're also now talking all together through Zoom. And the title is going to be something like either Higher or Brave New Arithmetic Duality. And as I said, this is definitely work in progress. And my plan is to talk first about a review of Poincare and Tate duality from a point of view that will be helpful here. Then I want to give a tentative definition of what we might mean by a higher local numbering. Then I will talk about an idea which I'm calling Drinfeld decomposition. Somewhere around here, we will have had a statement of the main theorem. And then towards the end, I will then try to say how we prove this main theorem involving a series of dualities that I'm calling Hodge duality, prismatic duality, and symptomic duality. Okay. So let's review Poincare duality in a special case. So let's say K is a field, and M is a closed, oriented n-manifold. Is this large enough? Okay, thank you. With a fundamental class, I'm writing a square brackets in M in the nth homology. Then the cup product, so going from the cohomology of M in the K coefficients, and the cohomology in the complementary dimension n minus star to the top cohomology, followed by evaluation at this fundamental class to K, is a perfect pairing. So this means that the adjoint map from the cohomology here to the linear dual of this space is an isomorphism, and vice versa if you interchange the rules. Now I'm going to talk about cohomology. I don't want to mention homology again, but I do need to mention evaluation on the fundamental class. So I need this homomorphism, and just as for the rank homology, this can be thought of as integration. So I'm going to write integrals for these evaluations on fundamental classes. So once we have that integration or evaluation on the fundamental class, we deduce that the cohomology of MK is a Poincare duality algebra. It is isomorphic to its linear dual with a degree shift of n. So this works more generally for so-called Poincare complexes. There's something called a Poincare pair, for which a closed manifold is an example, sorry, a compact manifold, and that's usually called Lefschetz duality. So if W is now a compact oriented n+1 manifold, so I used to go to these topology meetings in Oberwolfach where there were people doing geometric topology, and they were careful about this to say, but so compact means you have a allowed boundary, whereas closed means the boundary is empty. So here the fundamental class lives in the relative homology. And then you can express Lefschetz duality to say that the long exact sequence in cohomology for the pair like this, well, that is a long exact sequence, but I'm going to write it in a slightly unusual way, which basically encodes Lefschetz duality. So it's isomorphic to, okay, we're starting out the usual way. We're starting in the cohomology of W, and we restrict to the cohomology of the boundary. But now the boundary is a closed n-manifold. It's oriented by the boundary of homomorphism applied to this class. So this is isomorphic by Poincare duality to the cohomology in dimension n minus star when you take the linear dual. Now this homomorphism has a linear dual, which we can put over here. So let me write I check for that. And Lefschetz duality tells us that this is a long exact sequence. And so we could refer to this by saying that we have a Poincare pair, or motivated by the case where n is 2 mod 4, so that the middle dimension has a symplectic form, then this would be the inclusion, in the middle dimension would be the inclusion of a Lagrangian subspace. So we're going to say that this map is Lagrangian, or that the cohomology of W mapping to the cohomology of the boundary, when there is an implicit self-duality of this, I will express this by saying that the map is Lagrangian. I should say a lot of the ideas here are based on notes by Butt from some lectures on prismatic F-gauges at the Institute for Advanced Study 3 years ago. And this terminology is the terminology used by Butt and Lurie in that work. More precisely, I will actually be talking about maps in some stable infinity category, probably maps of spectra or something like that. And I'll say a map, and the target will have Brown common and self-duality. And by Lagrangian, I mean that I get a cofiber sequence when I take my map, followed by the dual map, like that. But that induces a long exact sequence in.
And the boundary map is induced by W? You haven't said anything about the boundary map.
Well, it's the map that you get. Well, there is a cap product with the fundamental class here, which is the usual statement for Lefschetz duality, and you have to invert that. Okay. A key case here is going to be the one where W is a cobordism from one manifold M to another manifold N, where the boundary here then will be the disjoint union. So this will actually be the sum of two-point Gray duality algebras, the cohomology of M and the cohomology of N, with appropriate orientations. Okay, and let's review Tate duality. So if I have a field F with algebraic closure F bar, there's an absolute Galois group, and this can act on various representations. For example, it can act on the p roots of unity of the field, or maybe the W's tensor power of that, and that is often written as Z mod P with Tate twist W. And now the Galois cohomology of the field is the same as the continuous group cohomology of this group, acting on the appropriate representations. And in a special case where the field is what we call a p-adic number field, so that is a finite extension of QP. So it has a valuation ring, which I'm going to write as OL. So you can think of QP, for example. Then there's the so-called Hasse invariant, which calculates a certain Galois cohomology group, and that specializes to an isomorphism between the second cohomology of the local number field with coefficients in Z mod P twisted once, and a Z mod P. And I'm going to think of this as a kind of evaluation on a fundamental class, like earlier. And the theorem of Tate, proven also by Poitou, says that if you take the cup product in Galois cohomology for a local number field with some twist, and you pair that with so that you land in the second cohomology with twist 1. And use this Hasse invariant, and this is a perfect pairing. So again, the Galois cohomology with field with these coefficients is a Poincare duality algebra. And there is something called a tall K theory. And so for a local p-adic number field, there's a descent spectral sequence going from this Galois cohomology to the mod P homotopy groups of a tall K theory. And this duality property given by Tate duality tells you that this is also Poincare self-dual. It's equivalent to a shift of its own Brown commonness, of the Brown commonness spectrum. Now there are other spectra around here. For example, there's the ordinary algebraic K theory, or we could look at the K theory of the valuation ring, or we could look at the topological cyclic homology of the valuation ring. It turns out there's a diagram like this, and actually all of these are, this is the K1 localization of all the three other objects. And the Bayliss and Lichtenbaum conjecture tells you, as proven by Wygotsky with Rost and maybe Weibel, tells you that this is a Lagrangian map. So this map followed by the self-duality followed by the dual map, that's a cofiber sequence. And calculations by Böckstedt and Madsen in the unramified case, and I did the Pareto 2 case, and then by Hesselhoff, Madsen in the ramified case, tell you also that this is a Lagrangian map. The notes by Batt and Lurie, they study this in the case where L is QP, and they develop this property a little further, and in particular they also prove that you have similar duality statements with more fancy coefficients than just taking homotopy groups. So these coefficients are these prismatic F gauges that I mentioned. So these are actually two distinct Lagrangian subspaces of the same symplectic space, if you like. Their intersection is what we might call isotropic. The pairing restricts to 0 here, but it's not maximal. So it's somehow a non-Lagrangian but isotropic subspace. And when I was thinking about these things 20-odd years ago, I spent a lot of time trying to make these two things be the same Lagrangian subspace, and that led to a lot of fiddling, which you now see why it didn't work out. Okay, so the aim, I guess, is to extend these kinds of duality results from the case of number rings, or rather local number rings, to what we might call higher local number rings, so ring spectra that have higher chromatic type. So together with Christian Arsoni, at the end of the previous millennium, we calculated topological cyclic homology for one of these local number rings. So we calculated the topological cyclic homology of the Brown-Petersen spectrum PP1, sorry, the truncated one, so we called it, that's the atom sum, and we calculated the mod P and V1 homotopy of this at large primes. The publication date is 2002, and we could also conjecturally make computations of higher truncated Brown-Petersen spectra, but this was hypothetical in the sense that it relied on the existence of structured ring spectrum structures that were not known to be around at the time. And the outcome of these computations, in particular that the result had pure V2 periodicity, led to the so-called redshift problem that I discussed in Oberwolfach in 2000, and which has since then been positively resolved by Hahn and Wilson in the case of all of the VPNs at all primes, and by Utlund, Schlank, and Yuan in the case of all, in a slightly more qualitative way, for all the infinity rings. But the calculations also suggested, by comparing with the kind of number ring situation where there was a Galois cohomology converging to a bigraded Galois cohomology, giving the starting point of a spectral sequence converging to algebraic K-theory, it should, that there might exist some sort of bigraded cohomology theory, at least for E-infinity rings, with a spectral sequence converging either to the algebraic K-theory or topological cyclic homology of that E-infinity ring. And moreover, it looked like this bigraded theory might satisfy a version of sort of a higher Tate duality. So I explained these things in a talk in Wuppertal in 2005. At the time, Walthausen's travel plans were not to travel, but he did actually send a student. So, that was... right. Now, but this envisaged cohomology theory has been constructed now by Hahn, Roxett, and Wilson. This is the so-called symptomic cohomology for ring spectra. So this is motivated by the work by Batt, Moreau, and Scholze in the algebraic situation, but for quasi-symptomic rings, but it has then been lifted to a class of what's called chromatically quasi-symptomic rings and algebras over those. So this arises as, so there's what they call an even filtration on topological Huxley homology, which for nice B produces a filtration they call the motivic filtration on the topological cyclic homology. And I think I said filtration, and I meant to say filtration. I didn't write it. Filtration. So if you take the co-limit of this filtration, it will map to TCOB, and the associated graded is now a graded spectrum. So this is actually a module over the associated graded for the even filtration on the sphere, which you may also know as the cofiber of tau. So this is the map inverting tau, and this is the reduction mod tau, if you like that language. And as I said, this is a graded spectrum, so it has the symptomic homology of B is going to be the homotopy groups of that graded spectrum, which is a bigraded abelian group, plus additional structure. And this will then be the starting point for a spectral sequence converging to the homotopy groups of TCOB. But you can also introduce coefficients. You can reduce mod P and so on in these stories. And then this sort of hypothetical duality that we expected from our purely hypothetical computations here has then been verified in the case of BPM by Han and co-workers and Devala Purkai at the level of these bigraded homotopy groups. When there's a computation, you can calculate that the algebra that comes out actually has the relations you need in order for it to be a Poincare duality algebra. But it would be nice to have a spectrum level statement and maybe a spectrum level proof of an actual spectrum level self-equivalence. And then there are further calculations by Sony on V1 homotopy of TC of KU, including odd primes. And this picture over here, which is a computation by, so this is a computation of the symptomic homology of real K theory with mod, so this is the sphere mod 2, 8, and V1, which I can think of as, which I'm going to write as the 8-cell complex A of 1. So this is a computation by Angelini Knoll, Sony, and myself. I guess the preprint is from 23. And actually what the dots here are, they are an F2 V2 module basis for the symptomic homology of real K theory, which is then the starting point of such a spectral sequence converging to the A1 homotopy of the topological cyclic homology of KO, which you can think of as basically algebraic K theory of real K theory with appropriate coefficients. And now my hope is that by this time you have noticed that there's a certain symmetry in this picture, and we'd like to have an explanation for that symmetry.
Sorry, what was A1 star?
So that's the, so A1 is a spectrum realizing the rank 8 subalgebra of the dual synod algebra, and if you take the tensor product, the smash product, if you like, of A of 1 with this and take the homotopy, so it's A1 homology. Yeah. So you know, if we're talking about horizons here, if you're at the Strait of Messina and you see this on the horizon, it might be a Fata Morgana, the castle of Morgan Le Fay, actually out on the island. But actually what you're seeing, you're also seeing a castle floating in the air above it. That's the Fata Morgana. So is it that? Well, obviously no, because here we see we only have one sign representation. This is a reflection, whereas this picture is we have rotational symmetry, so it can't be a Fata Morgana. It has to be something else. All right. So what can we do? I need some notation. So we have the Smith-Torre complex, which I'm going to write just as V. So V will always be the type N Smith-Torre complex, which is we thought of like this. So this is a spectrum whose mu homology is mu star mod the invariant prime ideal IN. which is actually a commutative mu star mu comodule algebra, which may or may not exist as a ring spectrum. But if it doesn't exist as a ring spectrum, at least it exists. There's a at least it exists because this is an even commutative mu star mu comodule algebra. There's an equivalence here with GR even S modules. So there will always be an E infinity algebra in GR even star S modules, whose mu homology is this. So that's rather quickly what we're going to be working with when the height is large. I need the Brown Combinates spectrum I, so that the homotopy classes of maps from any x to I are identified with the Pontryagin dual, so hom from I naught of x into q mod z. And in the cases where the v of n's don't exist, we're going to need a version of Miller's finite en minus 1 acyclic unification. Acyclicization. So if I have, so this is happening in the category of GR even star S modules. So if I have a graded spectrum like this with this kind of action, there's going to be a best possible approximation to it, which is called this finite en minus 1 acyclicization of x. This is the best possible approximation that is built from the associated gradeds of type n finite spectra. You can take any one type n finite spectrum f of n and look at its associated graded, and this will be built as a colimit out of those. This can also be thought of as the fiber of the en minus 1 finite localization in this category. Okay, so can we try to make a definition of, so here's a tentative definition of higher local numbering. I guess we'd ideally like to say what is a higher numbering, but for now this is entirely a local story. So first I'm going to start with, so I'm going to try to define a higher local number ring B. So it's going to be a regular local ring spectrum, meaning that B is connective. And it's implicitly P-complete for some fixed prime P. I'm going to take it to be an E3 ring spectrum or better. And I'm going to assume that pi naught of B, which is now a commutative ring, is a local ring, so it has a unique maximal ideal. And that has a residue field, necessarily of characteristic P. And the regularity, yeah, I'm going to ask that this is a regular local ring, by which I mean that K is perfect as in B module. Not as a field, but as a B module. There are a lot of words. The perfect has these three meanings so far. So it's a retract of a finite cell B module, if you like, or compact, or small. Okay, so that's what I'm going to call a regular local ring spectrum.
Why free?
Pardon me?
Why free?
Free.
E for E free?
So that when I apply functors like K-theory or THH, that I'd like them to be at least homotopy commutative. And there are multiple reasons. And then I want these to be of finite height. So we're doing sort of chromatic. We're not trying to discuss the sphere spectrum here. And in order for it to be higher, it should have positive height. So this means I'm going to let n be the integer so that it's minimal, so that the Fn homotopy, so any type homotopy of B is finite. here it doesn't matter which finite type n spectrum you choose. So this is what is called the Mahold. Says that the spectrum is Mahold-Resk FP type n minus 1. And this implies that it has height less than or equal to n minus 1. Now there's a class Vn. There's a Vn self-map of Rv. So if remember, V is my type n Smith-Torda complex, and either it has a Vn self-map or I work in this G or even star module situation. And this is then a type n complex, so we know this is finite. So in particular, Vn has to be nilpotent. I'm going to assume that it's actually 0. So this, for now, I mean, this works in every example we know, and for now that seems to be an essential simplifying assumption. In order to ensure that the height is actually equal to n, we may want to assume that this is a regular sequence in the mu homology of B. At the moment, as I said, it's a tentative definition, so there are some things where we're not quite sure exactly what we need at this point. Or what the minimal hypotheses are, so to speak. That's my question. Anyway, so by higher local numbering, I mean that I'm going to have a regular local ring spectrum which has a finite positive height. And then in order to allow the word number, I mean, usually that implies that there's something smallish about this thing. It's not huge, and that is implied then by, so a higher local number ring. It should have those properties here, and then we also require that this finite algebra actually is a Poincare duality algebra. So we require that there is an evaluation to some, do I want to say, maybe I want to do it in the spectrum level, some shift of the Brown-Common dual inducing on homotopy then a homomorphism from Vm of B to Q mod Z, which is like an evaluation of the fundamental class in the sense that it exhibits B tensor B as Brown-Common self-dual. So in the BPN example, for example, this will just be FP, which is definitely invertible. Sorry, Poincare self-dual as an FP algebra. But here, if this V does not exist, so that we are in this GR even S module situation, then we want to allow something slightly more. Then we want, so if the V does not exist, then instead we're using this E infinity algebra in GR even S modules. And then we don't insist that the evaluation lives on all of that. In fact, this is likely not to be a Poincare duality algebra as it stands, but we require that it is defined on this finite acyclification. And now we're in the bigraded situation, so there's going to be a second grading, and we call it n star, n prime. And this should now exhibit as what's called a Gorenstein. It should have Gorenstein duality. So basically, the Spani-Whited, this object will then be equivalent to a suitable completion of its Brown-Common dual, or if you like, but that's the special case that I know I don't actually have time to talk about.
John, I've lost track of. Are you still doing the definition?
Yes. So here's the end of the definition. I'm not sure what the correct symbol is, but that's the first one that came to mind. Yeah, so a higher local number ring has the properties on that board plus this. And we should have some examples.
In this last part, B really means this is a gradient of B in the even group.
Yes, very quick. Yes. Yeah. I'm sorry. Actually, no.
Can you repeat the question?
Yeah, the question was whether this means
what category is that?
in what category. the question was whether this is, I mean, so this is a GR even S module, and there's a question about whether this is implicitly tensored in each degree, or if it's tensored over GR even of the sphere with a GR even of the B. I guess it is tensored over GR even of the sphere with a GR even of the B. Yeah. So we have some examples, for example, the BPNs, or we can do KU also at odd primes, or you can do KO at the prime 2, but this is a case where V of 1 does not exist. So here the point is to make is that the finite acyclification is the same as the eta power torsion functor. So it's the local total derived local cohomology, meaning it's the fiber of the map that inverts eta. So remember, in this motivic situation, eta is not nilpotent, so this might be non-trivial. And there are versions of TMF for which this works, and also unramified extensions. Of all of these, where you join roots of unity of order prime to the characteristic to pi naught by the construction of Schwessel-Faulkner-Walthausen. Okay. So now I want to use this Nicolaus-Scholze presentation for TC. So we have a ring spectrum B. We have the cyclotomic structure map from topological Hoxsell homology to the CP Tate construction, which I'm going to abbreviate as T hat of B. So the hat refers to the Tate construction. I'm going to allow myself to follow the notation of Randy McCarthy. Question?
Very nice question. So in this situation, I wonder, yeah, this is a complicated definition, but I wonder whether it implies something like chromatically quasi-syntonic that you mentioned.
I have trouble hearing what you say. Can we take it?
I mean, this definition, does that imply any version of quasi-syntonic that you mentioned?
Does it imply quasi-syntonic?
Oh, if it implies quasi-symptomic, no. No, the examples, I mentioned chromatically quasi-symptomic. In practice, the chromatically quasi-symptomic will be handled by working with algebras over chromatically quasi-symptomic algebras such as the sphere spectrum, or MU.
So you mean this ring is not necessarily, these rings are not necessarily quasi-symptomic?
All the examples I'm talking about are actually,
because here you have regularity. I think, well, in classical commutative algebra, I mean, it's enough, but I'm not sure in your higher setting it is also.
Yes. I'm not going to be able to answer you right now. I want to introduce that. So this is what I often called TC minus. But I'm going to need a number of decorations, so I'm going to just write Tn for negative or Nygaard. So this is the circle homotopy fixed points. And then we have the periodic theory given by the circle Tate construction. And there's a comparison map from the circle Tate construction to the circle homotopy fixed points of the CP Tate construction. And for connective spectra, that is an equivalence. So that's going to be my gluing equivalence G. And then topological cyclic homology. Let's see. So this means we have so the negative topological negative homology, or TC minus of B, has a canonical map to topological periodic homology. And you can take the circle homotopy fixed points of the cyclotomic structure map. And as I said, there's a canonical equivalence G here. So it makes sense to talk about the equalizer of those two maps. That's the topological cyclic homology of B. And this now sits in a cofiber sequence where the connecting map looks like that. And I'm also going to actually work with finite coefficients, and then I'm going to omit the v. So I'm going to write v THH of b for the tensor THH of b, which means THH of b mod p through vn minus 1. So I'm actually going to work, so to speak, in the height n, or over the height n substack of the moduli stack of formal groups, or the spec of the sphere, where these first n classes are all 0. That's what the v coefficients mean. Right. And now I'm going to, the one definition I haven't given you is what I mean by a symptomic orientation of a higher local number field. But granting that definition, I think it will be easier to explain when I have talked a little more. Then we come to here's the theorem, which you could call higher symptomic duality. So I'm going to assume that B is a higher local number ring with a chosen symptomic orientation. So this will be a condition on one particular class in one group, which happens to be Z mod P in the examples I gave. Then, let's see, I might want to say something about the topological cyclic homology of B with type n coefficients, and I can either reduce mod by Vn and have type n plus 1 coefficients, or I could invert Vn and look at sort of telescopic coefficients. And I'm going to have a Brown-Comness duality spectrum. So there are three parts here, where the first is maybe in the main part. So there is a well-defined evaluation or integral, which I'm going to call it integral symptomic here, inducing a self-duality so that the reduced topological cyclic homology is equivalent to its own Brown-Comness dual in this. So here, maybe I should, when it's bigraded, it's implicitly the V star here. So, and this then means that at the level of homotopy groups of these graded spectra, these symptomic homology groups with these coefficients are self-dual. With the appropriate bi-degree shift. So this is sort of the analog then of the duality that you would see in Tate's theorem. Part B is to say that if you look at this composite, so if you think of this evaluation as coming out of the type n coefficients, then it actually extends uniquely over the localization. So there extends a unique extension of this orientation over that localization, and this unique extension induces a self-duality. Both at the spectrum level, so it says that you could replace reducing mod Vn here by inverting Vn and still have a self-duality. And again here, instead of reducing mod Vn, we could invert Vn. And so this would be actually much closer to the Étale cohomology or Galois cohomology version of Tate's theorem. And then there's the third refinement about how this unreduced story sits inside, and so one way to say it is that the pair of maps in Jn is Lagrangian. So this is not self-dual, but it maps to two self-dual objects in a way that gives this kind of Lefschetz type duality. And this is actually the point that is somehow emphasized in the notes by Button and Lurie, that they're able to give this filtered refinement of Tate duality in the number field case. So what is the main idea here? So
Before you, does A explain this picture in the A1?
almost, except here it was A1 instead of, if I take, it would have been with V of 1. Yeah, let me get back to that at the end. Right. So now let me get to this picture instead. So heuristically, we view the negative cyclic homology as the functions, the ring of functions on some geometric object. And this is one of the geometrization approach of the Drinfeld and Button-Lurie. So that's something they would call the Nygaard stack, or maybe we're looking at the part over the height n piece. And the periodic cyclic homology is then the ring of the functions on something which I'd draw much smaller, namely the prismatic stack. Maybe I should draw a little prism here. And the two maps from the topological negative to the topological periodic correspond to two distinct embeddings of the prismatic stack into the Nygaard stack, as this end and that end. And when we take the equalizer of those two maps, when we form topological cyclic homology, we're looking at the functions then on the quotient space, where we glue these two embedded things together through this equivalence G. So we form the symptomic stack as a quotient of the Nygaard stack by identifying those two subspaces. Now someone might complain that, but the prismatic stack is algebraic geometrically, it's a localization, it's an open substack. And I've drawn it as part of the boundary. And well, okay, so yes, so actually the Nygaard stack should not be thought of as a compact manifold. It should instead be thought of as an open manifold with cylindrical ends. So you take an open color of the boundary, which is like a cylinder, and then you remove the actual boundary, and then you glue this cylinder with that cylinder. You glue the cylindrical ends together instead of just the boundary components. But for the purposes of cohomology, if you're working with a closed manifold, or if you relative to the boundary, or if you work with the open submanifold relative to the cylindrical ends, it doesn't matter. So for cohomological purposes, it's the same story. Right. Now these computations of, that I guess I've erased, motivating redshift, they ended up saying, well, always the answer is always Vn periodic. There's always a redshift and there's no Vn torsion, even if there's lots of it along the way in the computations. And so there's an insight which is present also in the papers of Hahn and Wilson, that it may be better to actually work mod Vn. To set Vn equal to 0, and to work with, so if we first compute the homotopy reduced mod Vn, and then there's a Bachstein spectral sequence converging to the V of n minus 1 homotopy. But this means, and if the answer turns out to be free, it just means that this Bachstein type spectral sequence will collapse. And often you can prove that just by sparsity arguments involving the motivic filtration. So what this is saying is that maybe it's a good idea to reduce further and look at the case where we reduce also mod Vn everywhere. So this corresponds to something called a reduced stack in Drinfeld's picture. And now what happens when you look at a special fiber, sometimes it actually breaks up. And that's what happens here. That's what I'm going to call this Drinfeld decomposition. So here's a proposition that makes this work. So we can factor use the factorization of Vn as A lambda times mu n tilde. And this is now happening in the ROS1 graded ring given by the circle equivariant homotopy of V tensor THH of V. So, so here A lambda is the Euler class of the standard one-dimensional complex representation of the circle. And the other class here, this mu n tilde, so that lives now in the stem of Vn plus lambda equivariant homotopy of V tensor THH of B. And it has the property that if you forget about S1 equivariance, then you're landing in the 2p to the n stem of THH of B. Then it's a Bergstedt class. I'm calling mu n, so mu n tilde is the equivariant lift of mu n. And this has the further property that if you're mapping down to the residue field, we know that THH of k is polynomial on a generator in the 2 stem that I'm calling mu naught. And the Bergstedt class lifts that thing there. So this is the factorization we want to use. This argument uses the assumption that Vn map to 0 strictly. And the ROS1 grading is essential because these theories are not complex orientable, so I can't do this factorization if I don't work ROS1 graded.
You need a V in the middle, right?
Pardon me?
Don't you need a V in the middle?
I do need a V in the middle here, yes. Thank you. So then we get to kind of a higher version of, I mean, this idea is also present in some early work of Hesselholt and Madsen, but I think Drinfeld sort of stated it explicitly in one of his versions. And this is just the spectrum level version of that Stucky statement. So this is a kind of higher Drinfeld decomposition. So the first statement is going to be that there's a certain pullback square. So in my picture here, I factored Vn S1 equivariantly as a product of A lambda and mu. So I can reduce, instead of reducing mod the product, I could reduce mod just one of the factors, mod A lambda, or mod mu and tilde. And you have to be a little bit careful about the ordering here. I mean, take cofibers in the equivariance situation and then take circle homotopy fixed points or whatever. But now, by Shapiro's lemma, if you first take the cofiber for A lambda and then take circle homotopy fixed points, those operations cancel. So this is just the same as V THH of B. And the same thing happens here. So this is the cyclotomic structure map to V T hat of B. And then if we reduce mod both A lambda and mu n, well, then we're in a non-equivariant situation, so mu n tilde map to mu n, so this is V THH of B mod mu n. And the factorization tells me that I have a pullback square in the middle here. So geometrically, this says that when we're looking at the reduced situation here, remember this was the ring of functions on this big picture, but it's actually a pullback of rings, which means that geometry is a push out of spaces. So there's a subspace, a substack here that Drinfeld calls the Hodge stack, and Butt now sometimes calls the conjugate stack. And this CP-Tate construction behaves as the ring of functions on a piece that's then called the Hodge-Tate substack. And the negative cyclic homology mod mu n tilde behaves as the ring of functions on a part here, which is usually then called the de Rham stack. So we have now decomposed the reduced part here as a union of two substacks, or subspaces. And now we can actually analyze the gluing. Now we can think of the gluing process where these two ends were glued together in a slightly different way. Because at the beginning we first glued here, so we had this large part, and then we glued at the end. Now we're just going to do that in one piece. We're starting with the hard stack here, which is going to be a manifold. That's going to be the Oslo-Bergstedt duality. And this part, which is going to have the prismatic duality. And then there are two cobordisms. Those will be corresponding to Lagrangian theorems. One, and we're gluing these two cobordisms together along the common boundary to get a closed manifold. So its cohomology has Poincare duality. Right. So this change of view in how to do the gluing corresponds then to say that there's a co-fiber sequence at the ring spectrum level. It says that there's we can describe topological cyclic homology mod Vn in a slightly different way as the part coming from the Hodge-Tate, the upper part, and the Ron, the lower part, and these are glued together along the lower right-hand corner and the prismatic, if I like, part. Right, it does. And the combined gluing here is now given by this matrix. Right. So I forgot to put the maps in the name the maps. So F is the map that forgets circle invariance. I is the closed inclusion that corresponds to reducing mod mu n. J is the open inclusion that corresponds to inverting the Euler class A lambda. This map from the Nygaard cohomology to the Hodge-Tate is what's called gives the Hodge-Tate realization in the Bach-Morrow-Schulze paper, and the map here gives the Duram realization of prismatic homology. So those are the maps today. So 15 minutes, that's not quite enough. So the strategy now, I guess, is to prove self-duality for PHH of B mod mu n. So in the algebraic situation, that is what's called Hodge duality. It's a case of Serre duality if you're in the characteristic P situation. And this was studied by Greenlees in the sense with the label Oslo-Bergstedt duality. Slightly different hypotheses, but the conclusion is that there is an evaluation that provides a perfect pairing on this algebra, which sort of corresponds to saying that this space is a manifold. It's a closed manifold. And then we use the motivic filtrations von Ruxit and Wilson to deduce that we also have a self-duality for VTHH of B, well, for VT hat. So there's a prismatic duality or evaluation with the same bigrading. This is the part. So I guess I can put my. So the Oslo-Bergstedt duality gives us an evaluation here that produces a perfect pairing, and we can prove that the composite here always extends over the cyclotomic structure map. So there's always another evaluation on basically on the prismatic stack, so that this quadrangle that starts here and ends here anti-commutes. And saying that it anti-commutes corresponds to that there's then an evaluation, corresponds to there being a fundamental class in the relative homology of the whole piece that maps to zero. Maps to the boundary orientations. Or another way to put it is to say that the boundary orientations map to zero if you include them into the cobordism. So that's the anti-commutativity of that quadrangle expresses that we have an orientation form for the cobordism. And we are then left to prove that there are that the two things that behave, so these things have the homology of manifolds, and then we're left to prove that the other two pieces behave like cobordisms. So we have to show that the pair of maps I phi p to reduction mu. Oh yeah, and we also proved that the cyclotomic structure map here amounts to inverting mu n. So this is Lagrangian. So we proved that with in general for rings or equivariant rings, let's say R with the central element Z, we have a criterion for when does the map from R to R mod Z plus Z inverse R, when is that Lagrangian? And in this case it's verified because these groups, there's a certain double, you need at some point that something is a double Pontryagin self-dual. So that is verified when this is finite in each degree, is one reason for why we want some finiteness in this story. And then finally we need that that the forgetful map and the localization to VTHA to B mod mu n and VTP of B mod Vn is Lagrangian, which means that I have this equivalence capital G from the periodic cyclic homology through the CP Tate together with this prismatic orientation. So I get I can form the composite and get an evaluation also on the periodic cyclic homology, which is then necessarily also perfect because G was an equivalence. But I still need to know that this quadrangle anti-commutes. And that corresponds to, that's going to be the orientability condition. So I'm going to say that so the symptomic orientation, that means that we have a choice of this Oslo-Böckstedt duality with the property that when you look at the associated prismatic orientation, which was unique, determined by this first one, it satisfies that this lower diagram. So it says that this identity holds in the small group of homomorphisms from here to here. That group is just a copy of the ground field, okay? So it's an identity in the ground field. You have two elements in the ground field and you need to know that they add to zero. And that is implicit because here, remember the word Lagrangian involved a choice of Poincare duality structure on the target. And I need to know that the orientation of this piece and the orientation of that piece are compatible under this gluing equivalence G. I need somehow to know that I didn't produce Klein bottles here. I produced orientable surfaces. Right. But yeah, so once one has these things, once you know that the Hodge part is a manifold, the prismatic part is a manifold, the Hodge-Tate, the upper part, is a cobordism, and the Duram part is a cobordism, all to the eyes of cohomology. It's then a formal diagram chase from this cofiber sequence to deduce that indeed the topological cyclic homology is also self-dual. So basically what it proves is that then now the two maps that were being equalized in the definition of TC, they agree as maps to the Brown-Commonist spectrum I. So the composite is 0. There, if you take the difference, the composite is 0, and therefore there is an extension here, which is the. So this is basically Wall's gluing lemma for Poincare pairs, saying that when you glue two Poincare pairs like this together along their common boundary, you also you obtain a Poincare complex. And this is the evaluation form, evaluation on the fundamental class for that Poincare complex. So this is the, we still have a theorem. Yeah, this is the symptomic evaluation that induces this self-duality either at the level of spectra or at the level of symptomic homology groups. I think I'm not going to, so there are, I guess I kind of packaged section 4 into this. Yeah, so what about this example? So what happens here is not quite, so what happens here is that we get a pairing from the one homotopy of TC of KO with the eta power torsion of the V1 homotopy of TC of KO into the eta power torsion, which induces an equivalence between the V1 homotopy of TC of KO and a suitable eta completion of the V1 homotopy of TC of KO. I think the numbers here are 10 and I guess when I'm at the TC level, it's going to be 9 and 3. So the adjoint of taking the eta power torsion, or the Brown-Commonist dual of taking eta power torsion is going to give me eta completion. And now this equivalence, these are not finite, but if I reduce mod eta on both sides, V of 1 mod eta will give me the, yeah, so I guess I should have had 11, okay. This is how the self-duality in this picture arises as, well, okay, I actually want to reduce mod V2 as well. This is a little bit analogous to how I only stated a special case of Tate duality involving the Hasse invariant on p roots of unity, but it is actually defined on as a cohomology class, or it's a computation of the Galois cohomology with coefficients in the multiplicative group scheme. And in the same way here, you need somewhat more general coefficients in order to capture this, this duality in this special case. Anyway, I think I've spent my time. Thank you very much.
Questions?
How do you determine these bidegrees for the duality?
The question was, how do we determine these bidegrees for the duality? Right, so that's a problem. That's part of why we may need additional hypotheses. Of course, in the concrete examples, we can calculate them. And in fact, in all the concrete examples, the n prime, the filtration bidegree here, coincides with the redshifted height n. But we're not currently sure what the correct hypotheses on B are going to be in order to ensure that that always happens. It's a little mysterious in the KO case, precisely why these things fall out. It looks like this may have to do with facts like that if you have a homotopy commutative compact Lie group, then it's a torus, or similar, or that actually works for p-compact groups, that sort of a thing. So there's something behind there. So for the moment, I don't actually know that n prime is always n, but it's expected. It is, I mean, this bigrading, this is something which all comes out of, this is all a statement about this original Oslo-Bergstedt duality. So it's only a statement about THH. So I should say this corner is pretty computable. This is sort of the relatively easiest, this is the easiest corner. So, so it's not super hard to find, yeah, in the examples it's not so hard to find, but yeah. It's an open problem whether n prime is always equal to the redshifted height n.
Anyone else? John,
how about the hypothesis of orientation? Is it a hypothesis or is it something? Is it just a choice? For example, a symptomic orientation.
So it is a hypothesis. For the moment, it's an hypothesis. It's a hypothesis about two. It's about a class in the. Yeah. So in the homotopy classes of maps from B tensor HA to B. Well, it's actually isomorphic to. So the top stem and motivic filtration of THH of B is a copy of K with a choice of generator, but not a canonical one at the moment. And this amounts to a homomorphism, the integral AB here. And there's some endomorphism of K. And so orientability, there's some endomorphism of K, so that the condition is that that endomorphism followed by the evaluation is equal to the evaluation. And we believe this endomorphism is the inverse of the Frobenius automorphism. But I don't know how to prove that. It's a sort of a green flash theorem. If you're on Ocean Beach in San Diego, sometimes at sunset you can see the green flash for about a second or two, and that's how long my proofs last. But it's a single group. It's a small. Feels like so. It is an orientability condition. It's plausible that every our local number ring is orientable in the sense that this works. But I don't have a proof of that yet. But it is somehow a much smaller condition to check. Again, it's a condition on one of these groups that is relatively easy to calculate. I should have written mod UN here, sorry. And of course that, I guess that's another Walthausen quote, don't confuse me with examples. The problem is, I know the examples too well, so it's hard to tell what is the feature of the examples and what is true in general. But it is in the prime field case, it is relatively easy. So it's easy to verify in the prime field case. When K is FP, this Frobenius automorphism issue is not there. So it's just a question about whether you can lift that class to topological cyclic homology. So there's a map from topological cyclic homology to topological Huxley homology. And we have this homomorphism to Z mod P. And we have a particular class that maps to 1. And we need to know that the composite from here is non-trivial. So we need to lift that one class to topological cyclic homology. And in practice, we often have presentations of this top class as a product of things generated by power operations. That's one reason for assuming E3, so that these are E2 rings, so that there's the power operation you have in E2 rings. And now, if you can, and we also have the same power operations here. So if you have a sort of a formula for this here, you can lift the formula and produce the class up here using the power operations in TC. And actually, it's enough to do this. I mean, it feels like, okay, now maybe this is circle equivariant, maybe that is hard. Well, it's actually enough to get it up to the CP equivariant version. But it's still something one needs to prove.
All right, let's think. I think we should spend a long time since.